Alright, time for another dratphysics.com, debatephysics.com, also video presentation. So I thought, since it's a little off day, just do overviewing and some of the different experiments and the evidence. Alright, so I think it's important to first go with the history, okay, and what there was that started the whole thing. And so the first argument was made by Leibniz as kind of a little catchphrase that 4 pounds, okay, dropped 1 foot, okay, does equal, well, that's 1 foot. Anyway, the same impact or power or energy or force as 1 pound, okay, dropped 4 feet. Alright, now that experiment really hasn't been done, but it's basically saying a quarter mass at twice the velocity, because the 4 feet would be twice the velocity. It's a well-established fact. So, a quarter weight, twice the velocity equals a full weight at 1 velocity. I think everybody would agree that doesn't happen. So this was a poor foundation for mv squared being true, and it's pretty much the only piece of evidence Leibniz argued from was this axiom, this assumption that this was in fact true, that it took the same work to lift 4 pounds 1 foot as it took to lift 1 pound 4 feet. Now, depending on how you lift it, they can always equal each other, because you can always make it harder to lift. You can do more work, that is, you can lift it slower, the 1 pound, and you can make it into more work, and then make the two things equal. But based on their gravitational falling speed, their ideal speed, their most efficient speed to go with the exact distance, that velocity, against gravity, will not indicate that they have the same energy. Alright, then you have the Descharlet clay experiments. So they dropped round objects into clay, and the catch was, when they dropped them, they just dented the clay. Okay, so the clay was never penetrated deeply. It was just superficially impacted. And the fact is, this round surface means for an object that impacts less, it's doing more work, in the sense that it has to push down into the clay and then push that clay sideways, where the thing that goes deeper is doing more pushing the clay just sideways, using the round surface. The direction of the push changes as you change the surface, and the less of this you're doing and the more of this you're doing less, you're using less energy per unit of displacement. So this is garbage, pretty much. This is kind of garbage. And so now we're all the way into the 1800s, and this is all they have so far as any kind of evidence. Alright, and so now we'll just talk about the talking, because they pretty much stopped doing any kind of, oh, sorry about that, that could have been better aimed. Shit happens, as they say. I think you got the idea. It wasn't that complicated. Alright, and so I would argue the biggest piece of missing evidence right now, the thing that would be really, 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 really decisive, is if they could fix this to, twice the velocity, 4 times the fuel. Okay, so you have to put 4 times the fuel in to go twice the velocity, and then if you move something twice the velocity, it does 4 times the work. Okay, so, and then you just take that to its ... conclusions, and it ends up being a theory that states that 25 times the fuel will get you to 5 velocity, and that 5 times your velocity will somehow produce 25 times the work. You'll bang into things and move things and cause and effect that is in its magnitude 25 times greater than the magnitude of going one velocity. Doesn't seem realistic. 25 times greater just doesn't sound quite right. It will be 25 times. It'll be 25 units of work. Alright, maybe that's a better way of saying it. Yeah, I don't know. The one velocity produces 1 unit. The 5 velocity produces 25 units. It is 25 times. Anyway, alright, so we have no evidence of this. Just nothing. Okay, nothing to indicate 4 times the work. Alright, now there's a simple rolling experiment that is sort of implied to be meaningful in the sense that you can roll the same object on a surface, and I always tend to give it way too much credit, and you can have 1 velocity versus 2 velocity, and it will in fact roll 4 times the distance, more than 4 sometimes, but there's a reasoning, there's something logic, you can understand why that might happen, and it's pretty much entirely Galilean in terms of Galileo already discovered the truth about what's really going to happen. And the 1 velocity will happen here, 3/4 of the way down the track. Alright, because you are higher velocity means you will in fact be pressed less, you'll weigh less on the surface per inch, and you'll weigh more per inch here. And that this in fact will be a unit of time, 1 unit of time, 1 unit of time for this, and this will be the same. I didn't exactly draw that precisely, frankly, but anyway, this adventure here will be exactly the same as this, and that this one will also equal the same thing. It'll be 1 unit of time, and it'll be 1 unit of work. This will 1 unit of work, this is 1 unit of work. So twice the velocity will only get you 2 units of work. It'll only get you 2 units of time. You'll only take twice the time to go 4 times the distance. You'll only be in the gravity twice as long. So lots of 2's, 1 4, and the 4 is, you know, it's a mistake. Okay, it's a mistake to think that's the truth. That's the controlling factor is the 4, when the 2 units of time are clearly in control, and it only produces the 2 units of work. Alright, so that has been done, has been argued. Again, these are arguments made on the debatephysics.com website in 5-minute videos detailing these a little bit more, not much more than this, but a little bit more. Alright, so let's move on to now the collision experiments that aren't very useful. Now we don't have anything directly from space, but we do have testimony about space and what happens. So I suppose it could be argued that I don't think there's any arguments made by any physicist regarding navigating in space, that is when you're outside of atmosphere, and how basically what's going to decide, I won't even bother, you could say this is a rocket ship, it doesn't matter what shape it is, that the only way you move this thing is by throwing essentially mass and at a velocity. So you're throwing a mass, and all that really matters is the mass that you throw, the weight of the particles, and how fast are the particles moving. And there is no mv squared in space in terms of navigating. Therefore, the speeding bullet shot out one side, and the recoiling gun shooting out the other side. I think physicists universally will say that this equals this, because the momentums are the same. Now, the kinetic energy theory says this has 2,000 joules of energy, that it can do 2,000 watts of work, and this can only do 2 watts of work. Okay, that's what they'll say. They say is true, but they'll say, okay, it doesn't matter in space. In space, momentum rules, and kinetic energy is apparently useless, meaningless, really can't be used. You can't land on the moon with it. The theory won't help you navigate a lunar module or something. It won't in any way benefit you. So even if you're going to say it's true, okay, that this actually happened, and that somehow you manufactured that inequity and yet had the same momentum, it isn't useful. It doesn't make the thing move. So how can it really be relevant if 2,000 joules can't, if you can't tell the difference, if this spaceship can't tell the difference between the thing that has 2,000 joules that's shot one way, and it's not going to do an equal and opposite reaction. It's not going to equally and opposite react to those 2,000 watts that's going this way, and the only 2 watts going that way, and it's not going to notice the difference. It's kind of hard to argue that there could possibly be a difference. All right, then we have these group of experiments that all indicate something. So one is pendulums. So that's been done. It hasn't been done. It's been stated to be done. Okay, and I think the masses were 1 to 3. Okay, so you're letting a one mass, you're going to put the energy in with the one mass, and you're going to allow the 2 objects to collide, and you're going to end up with a circumstance where you're going to have both objects will move. Okay, now it won't be an even transfer because of the uneven mass, and you will have a circumstance where they will share the kinetic energy, I believe, or share the momentum. I have to think about that. Thinking, yeah, forget it. We'll just say, look, there's 100 momentums going in. What I'm going to end up with is 150 momentum going this way, and I'm going to end up with 50 going this way. All right. So by my logic, that's the creation of momentum, because you start with just 100. And what does direction have to do with it? Right? If I have a car crash, nobody sits there and calculates that, the fender went this way and the rear view mirror went that way, therefore those things cancel, so they're not part of the momentum equation anymore. I mean, that's how nonsensical it is, right? I mean, if I took a car and I actually did crash it into a pole, and pieces of it flew off this way, and some pieces flew off that way, and some pieces flew off this way, and some pieces flew off that way, I wouldn't say that, these don't count, and this doesn't count, and this doesn't count because there's an opposite, something going the opposite direction. I wouldn't cancel that and then say, the car crash only created, say I went in with 100 momentum, and then I calculate all the pieces and just try to find my 100 again, and only found 2, because all these cancellations, all the cancellations mean there was only 2. I know that all of these 5s here and the 50 here and the 25 there, and I know all those are going to add up to 100. I know in the end I'm going to have the same amount of matter moving, and it's just going to be smaller pieces moving faster, or can't really have a bigger piece, or big pieces, generally big, moving slow. And when I add up all those pieces and all that motion, I'm going to have mv here, and it's going to equal mv out. Mv in is going to equal mv out. Now, I don't know if I have an experiment I can show you. I can just indicate that lots of crash tests have been done, and they're usually analyzed through momentum is used to analyze them. And you do have a Mythbusters thing where they actually did crash cars at 100 miles an hour and 50 miles an hour, and the 50 mile an hour car crashed that much, the 100 mile an hour twice as much, not 4 times as much, just twice as much. So you have some indication that momentum is consistent, and there really isn't any evidence of kinetic energy being consistent. So anyway, back to this. So this idea that you can cancel this 50 by saying there's a 50 going the opposite direction, I think is a little bit nonsensical. Anyway, when these two things come back together again, the fact is they will collide, and only the one will fly back again. So the light one will fly back off with whatever, 99% of the original 100, 98, 97, who cares? And the 3 object will be stationary. So you just get back the 100 you started with, theoretically. You know, in a low friction circumstance, you just end up getting back what you put in. But you have this weird part here in the middle, all right, where you have 150 coming in and 50 coming in, and you're saying that's like a car crash. So if I had a car crash between 2 cars and one's going 50 and one's going 150 miles an hour, I don't have any expectation that these numbers are going to cancel and that the crash will only be a 100 mile an hour crash. I have every expectation that the crash is going to be a 200 mile an hour crash. That you're just going to add these numbers, okay, as real momentum, and whatever flies out of the crash, you can just add it all up, and it's going to have to add up to 200. So how did I put 100 in a crash? I get 200 out in a crash, and then I go back to 100 again. So, you know, it's stated to be a real phenomenon, okay. We don't have really great evidence that this ever happens. Now, physicist Michael is supposed to do this experiment with a big Newton's cradle, but it doesn't look like he's still interested. So that one will have to be left where it is in its current condition, okay, which is, yeah, I'm not sure. You know, I haven't seen good enough evidence. So, take a little break and erase, and well, I can erase probably without taking a break. Alright, so another simple experiment that's almost, it's, you know, been done many times, but it confuses, you know, in terms of, it forces one to come up with a theory that, you know, has to account for the fact that you are, basically, you know, you have a one mass, and then you have another one mass, and you're going to end up with a 2 mass, okay, 1 plus 1. And the idea is that when you have the one mass and you give it 10 velocity, when you combine these two, you'll end up with something that comes out that has 5 velocity, twice the mass, half the velocity. And, you know, momentum says that makes perfectly good sense. And the experiment happens. You combine these 2 objects. Now, in most cases, let's just say most experiments, when they do this, they don't collide the cars. I mean, they don't force this one to push this one, but they do this on an air track, you know, with Velcro, and it does come out pretty close. It comes out even better, though, frankly, if they just drop the weight on a car that's passing by. And you could sort of understand why it would come out better, is because the combining energy, when you're combining the 2 cars, doesn't have to come out of the original momentum. So the car moving, okay, the one mass moving this way, you know, if I combine 2 cars, all of the motion has to come out of this energy. There is no other energy in the experiment. But in this case, I'm adding gravitational energy. So I'm adding a little bit of gravitational potential energy, you want to call it that. I'm adding a little bit of motion created by something falling in gravity. So I have this velocity, you know, I have a vector going this way with a mass, and I'm going to have another vector adding, okay, smaller, much smaller vector, where I'm going to drop some energy in. All right, and the fact is the energy that combines the 2 objects is now free, in the sense that you didn't have to come out of this. So you didn't have to slow down to create the contact and the absorption of the second object, the combining. So you can understand, and it is true, frankly, okay, that if you do the experiment this way with little carts, that they do conserve, clearly, yeah, I could almost argue 99% of the momentum. I mean, hugely close to a perfectly conservative experiment in terms of you do retain the substance of the momentum. So the problem is the kinetic energy, you lose 1/2 the kinetic energy, guaranteed, at least 1/2. So the fact is you lose more because of this 99 number, and in the case of banging the cars into each other, it's probably going to be more like 97 or 96. So you're guaranteed to lose more than half the initial kinetic energy, the KE of the object going into the experiment. You're going to end up with half the KE coming out. And I've sort of pointed out that for me the experiment is just like me saying that, I have, $10, we'll call that my velocity, and I give somebody equal to myself, frankly, I give them $5. Well, when I give them $5, then I only have $5. So now we have two people with $5. And frankly, that's the same thing as the one person with 10. Okay, the two things equal each other. One person with 10 going to the store is the same, okay, as two people with 5, as long as the two people are buying the same thing. If they're going to put the money down on the same thing, if they're moving in the same direction, at the same velocity, then you might as well think of them as a 1 with a 10. There's just no other reason not to do that. You haven't done anything special. It doesn't take any work for me to give somebody $5. And clearly, it doesn't take any equal and opposite reaction for me to now be $5 poorer. I'm automatically $5 poorer if I give somebody $5. So that seems to sum it up pretty clearly. Now the key is if they try to argue, and they do, physicists will actually say this, the kinetic energy, half the energy, more than half the energy of the system is lost to explosions. Little pieces flew across the room and all kinds of crap happened. It was a terribly loud sounds, and just imagine a 5-ton train going 10 miles an hour. Half its energy, a tremendous amount of energy. You could bend metals, do all kinds of stuff. It's a tremendous amount of energy. And frankly, even if I did this experiment with 5-ton trains, just to be some sound, to be a little bit of bang, bang, bangs, but I'm still going to get the same result. I'm going to get all of my momentum is going to be conserved. And so the argument is, how could I send things into space? How could I shoot pieces off? How could I make sounds? How can I vibrate the ground? How can I do any of that, heat anything, if I didn't use momentum? If I still have the same $10, how can I give 5 to somebody else? Can't really do it. I can't keep the money and give away the money. And this combination, when I make this, when I give this $5, if all of a sudden a bunch of $1 bills comes flying off, I got $1 going there, and $1 going there, and $1 going there, and $1 going there, and a bunch of pennies flying out in terms of sound and heat. Well, how can I still have $10? Doesn't make any sense. So how can I deform and make sounds and just break metal and make sparks if I don't use any of the momentum? So that's a real dilemma in terms of making rational sense out of it. Alright, so continuing in the difficulty of transfer. So we do have spring experiments, but I don't even know if I want to try to isolate all of them into any conclusion, because there just isn't any. There's lots of conflicting experiments. So the simple experiment of, say, you have a 1 mass. Let's just make it a 2. Okay, you have a 2 mass, and you drop it the 1 unit of distance. Theoretically, okay, it's 1 velocity. If I drop a half mass, okay, I mean a 1 mass, half the mass, which would be 1 mass, from 4 times the distance, right, I'm going to get twice the velocity on impact. So I'll have a 1 mass going 1 velocity. Now, in one case, this experiment demonstrates that these two things are the same. They'll push a hunk of Play-Doh the same amount. And in other experiments where they use a spring, their claim, the results say, this spring is compressed more, okay, over here. Now, it's, debatable what the more amount is, but it's supposed to be twice the energy, and I don't think there's anything that comes close to proving that. But there are experiments indicating that that it doesn't come out the same way, that this somehow does have more capacity to compress a spring. So this is a light object having more capacity, which, you know, they claim the lighter objects are harder to move. So, we have the lever experiments too, but again, they're a little bit more complicated than we at first thought. So, maybe I'll think about whether there's much point in going any further with those experiments. I guess the coupled oscillator is the most recent one, and that one seems, pretty simple. Okay, so you have a 2 mass and a 1 mass, and you're basically going to put energy in. You can put it in on either side. And the idea is the oscillator basically switches the energy from one side to the other. Now that's the open question, is depending on how you do the experiment, whether or not that's what you're going to actually do. So in cases, you can do the experiment like this, where you basically couple where the couple is permanent. Okay, that is, these two pendulums really aren't independent ever. One can't really move free of the other. And then you can do the experiment where the coupling, is less guaranteed or severe. That is, there's just a weak coupling. And these pendulums are always at this arc. Right? That is, this string never bends. There's never enough tension between them to cause this kind of motion. So they're always in their natural condition. That is, the center. So the center of this pendulum is not going to be the same as the center for this pendulum, especially if this whole rack is moving. And so what you're really doing is changing where the bottom of the swing of the pendulum is. So if the pendulum starts with this long swing and then it's bent, the bottom for that pendulum has now changed its location essentially. And so now its peak velocity might be here, because you're basically changing the height of the pendulum by changing the length. By putting that kink in it, you've taken a line that's this long and you've shortened it essentially by putting a kink in it. Okay, this line is longer, it falls farther out than this kinked one, you can sort of understand. So if there's anything kinking the pendulum, it makes it's rising and falling, and that's going to change how it functions. So again, but these are subtleties, and this is a little bit complicated, but preliminarily, the results are indicating that kinetic energy moves back and forth. So somehow, when you put the energy in one way, that is, you swing the heavy object. So I guess I could just redraw that and make it clear and easy to see. So if I have a 1 mass and then the 2 masses over here, so I initiate the action here. What I'll end up with, is I put 100 momentum in. That is, I have a known amount of gravitational potential energy. It swings back and forth, and then through the coupling, this one acquires the energy slowly but surely, and when it's oscillating, it'll have 150 momentum. So I'll be making free momentum again. And then when this one stops oscillating and this one starts oscillating, the lighter thing again will be stuck with just 100. So when the energy is in the heavy object, it has 150 momentum. When it's in the light object, it only has 100. Now, kinetic energy theory says this this 100 momentums is the same. How could it be the same? It's really hard to say. But anyway, this because of the speed is the same as this, because this is only going 1.4, so it's only going 0.4 faster than this does. So this heavy mass ends up oscillating almost, only 0.4 short of the speed of the first mass. So it's moving really quite fast, and that's why it gains this extra momentum, is because the velocity is very high, much higher than you would expect if it was momentum and control. So you end up with the same kinetic energy by theory, you've conserved the kinetic energy, but you clearly have destroyed the momentum. And the key is this change in momentum is in the same direction. It's 100 this way, and it's going to be 150 this way. And so you can't use some mathematical trick and say, well, the momentum's cancel or something. This is just clearly free momentum. So that does make it doubtable that there's not something wrong with this experiment, but that's to be figured out yet. So just pointing out that these experiments are kind of noisy in their outcomes, and that there isn't a huge consistency. So there is another experiment by physicist Michael, where you take the same force in a spring, that is the same compression of a spring, and the heavier, you could presume, I mean, he only does it with one set, but we could assume numerous versions of it. But the basic idea is if I put a one mass here and a one mass here, and I get a total of 100 momentums going that way and 100 going that way, for a total of 200. Alright, and if I put a two mass on here, alright, I'll get 400. So I'll gain more force out of the spring. So somehow there's something causing the spring to fail to be able to push the lighter object, indicating again some sort of kinetic energy thing. I don't know, it's almost reversed, right? You have lighter objects moving slower. That's not going to be more energy. Well, no, they're moving faster, they're just not moving as fast as they should. So yes, they're only going 1.4 again. Okay, well anyway, so this was 200 and this was 200. Alright, and then yeah, so how far do you go with this though? So if I do a 3 mass, you know, am I going to get 600? You know, do I keep increasing how much total momentum I can get out of the spring by just increasing the weights that I put on either side of the spring? You know, apparently there's going to be a point where the weight's too heavy to push on Earth. Now in space, nothing's too heavy to push. So in space, I should be able to keep increasing this amount of momentum, you know, into really huge, gigantic numbers. Like we're talking about, you know, I go from, you know, tiny things to big, gigantic things, like whole space shuttles should be able to be pushed by the spring with incredible momentum. And then, you know, if I go smaller, like you would think bullets, you know, bullets fly out of guns really fast, so it's really easy to get the energy into the small little thing when you use a gun or explosion. Yet the spring does exactly the opposite. So the theory would be is that if I go smaller and smaller and lighter, you know, a half mass and then a quarter mass and then an eighth of a mass, I go lighter and lighter, I'll be getting less and less momentum out of the experiment until I got nothing, till the spring produces no energy at all. Obviously it can't do that because the spring itself has to move, but it can push nothing. A grain of dust will be too heavy for it. You won't be able to give it any velocity at all. So it's completely unintuitive. I mean, this experiment does pretty much contradict this one. And so it's all very mushy, very sloppy, and you know, again, so the real point is that the definitive experiment would be them to do to take the joule machine, okay, to take some device that can convert something's motion, an object's motion, into thermal energy, and calculate exactly how much thermal energy, how much thermodynamic activity it has. Because I would argue all motion is really heat. If I move this in a direction, it's really just heat in a direction. It has a certain number of watts. It's almost like a laser beam. It's just little pieces of matter moving that way, and it's doing it all in the same direction. So it's just heat with one direction, and the heat we call waste. Well, it's waste because it's going in all directions, and that can't do any work. It has to go in one direction to do work. It has to go in one direction in most cases. Obviously I could put something inside of a vessel and pressurize it and do work in all directions, but I could take that pressure off in one direction and do work. So it's not, you know, it's not a law. that one direction does work and any direction doesn't. Obviously in the gun example, it does work in two different directions. So, continuing with what example was, where was I? Damn it. Yeah, well, I've lost it temporarily, so I'll see if I remember, and if I don't, we've probably said enough anyway, but we'll see. I don't know, but I think I was heading for the gun example, where the spring can't move the light thing, and where the lever, they kind of imply that levers can't move light things either. They would put a 1 mass out here, and I put a 2 mass here. This motion can't create twice the velocity in this, so I can't conserve the momentum, because that would violate kinetic energy law theory, and so this has to leave with 1.4, so I have to kill the momentum somehow, and that's their theory, that somehow this has some sort of inertia problem. Light things are hard to push, and like I said, the gun kind of defeats that argument. And you can take the gun example, and just recognize that it doesn't make much sense, because there's all kinds of guns I can have. So I can create a gun, with just 2 bullets, but just 1 charge. Okay, 1 bullet doesn't have any dynamite in it, so it's the same amount of force, and the same explosion. 2 bullets. I'm going to end up with, let's just say, 1,000 joules and 1,000 joules. All right, no problem. Now if I make the gun, one side is blocked, okay, so it's a regular gun, and we have the 1 bullet, I'm going to get 1,000 joules out of the bullet and only 1 joule out of the gun. And then the third example would be is I could take 2 guns, and I could put 1 gun inside the other gun. Okay, and all I'm going to get is 1 joule and 1 joule. Alright, so the same force, keeping all of its energy in the system, or accounting for all of it, produces all these different results, from 2,000 total joules out, 1,001, okay, and 2. So I get these very different outcomes when I have accounted for all of the momentum, all of the energy of the explosion. So all of them have the same momentum, so momentum's conserved, no problem. But obviously these joule numbers don't match. The KE formula has huge variation, 2 to 2,000, as a realistic, sensible outcome for the experiment. And I would argue, come on, that needs explaining. Yeah, that doesn't make any sense. Alright, so that's probably enough. I've been over it so many times, but I'm just saying that clearly the evidence is murky. This is a very dirty pool of evidence. And so we're at trial, we're being forced to have the trial, alright, before anybody's done all this prep work. Okay, the investigators haven't analyzed the DNA, they haven't analyzed the fingerprints, they haven't done any ultraviolet light tests looking for dirty fluids. They haven't done anything, okay, to shore this up, and all we have is a couple of guys decided to shine a light bulb on something, didn't have an ultraviolet light. They put a couple of weights in their hands, they tried juggling on them a little bit and see if they all, if it worked. They messed with it a little bit. Took some masking tape and tied a couple of things together and swung them around and said, yeah. Alright, but that's all we have. And so we're sitting here at trial, we're arguing, and we just have kind of very little credible stuff to argue with. And frankly, that's how it's been for 350 years. Leibniz started with a garbage axiom, just a statement that wasn't true. Then de Châtelet showed up, did kind of sloppy experiments, and essentially threw things into sand. And she did different things that, yes, if you engineer it right, it'll come out your way. If you do the experiment a certain way, it will come out and give you any results you want, essentially. And these were the kind of experiments they did. They found a way to do the experiment to make it look like. Okay, so I can drop a ball bearing on an anvil, And if the anvil, it hasn't been heat treated and it hasn't been polished, okay, so it has a very hard surface, very flat, very hard surface, then I can drop a ball bearing, it bounces 4 times and rolls. Same exact drop on the anvil that has been heat treated and has been polished, and the ball bearing will bounce 200 times. So I can do 2 experiments, get completely different results. I can pull the rabbit out of the hat or pull, a butterfly out of the hat. I can pull almost anything out of the hat with some experiments, depending on how I do the experiment. That should be understood. That you can't, you have to be careful to understand the important variables. And with hard objects, elastic, things we call elastic that are hard, it's really important that you not fall for the fact that, oh, it's hard from my perspective. No, hard means a specific thing. It means it's not dentable, that it's not going to deform in any way. And that's a key. That's why things like glass are very elastic. It's because, it doesn't dent easy. It's pretty hard to dent glass. All right. So, that has to be understood here. And that context has been completely, in my opinion, ignored by the defenders, of the kinetic energy theory. They're just cheating and saying that, yes, we have a few sloppy experiments. We don't have any well done experiments. And they just are so cheating the truth not to admit that that's the state of things. So anyway, they're claiming that everybody has already proven all this. I mean, a physicist Michael even said, they've already done all these experiments. Again, I could claim they've never done the Eddington experiment. What will they say? Well, we've done all these other experiments that are just like it. Well, no, they're really not just like it. They're not anything like it. They're completely different experiments done completely different. They threw jelly beans at a wall and said that's the same thing as throwing ball bearings at anvils. No, it's not the same thing. So anyway, that's enough of a video, I think. So till the next time and such, and so forth and whatnot.